Hello, good evening. So,
Good
welcome
evening,
to
sir.
this online session on modeling and simulation of dynamic systems. So, this is
Good evening,
Jaswant
sir.
speaking. Yeah, good evening. So, so before we start, so I would like to ask whether any one of you have any specific questions or comments related to the content for this week.
Yeah, I have some questions on the holonomic and non-holonomic constraints. That
Okay.
concept, I was not able to uh, get it actually. So if you can
Okay.
explain little on that part,
Okay.
it would be useful. Yeah.
Okay. I'll try to explain to the best of my understanding.
And one more is like in the second tutorial, that is the simulation of that pendulum using
Mhm.
Simulink.
Yes.
Uh, with the example I tried, but somehow I'm not able to uh, get the result
Okay.
properly,
Which example are you mentioning?
which was told by the professor in the lecture.
So okay, so let me just open up the
Yeah,
slides.
maybe the basic thing also is fine. I was able to construct the models for the other cases.
Okay. So okay, fine. So we'll actually try to do that also in this session.
Okay.
So so can you just I'll just go through the slides one by one. So let me just know which part you mentioned that you are not clear.
Okay. Can you go down to the nonlinear part of the?
This one?
Yeah. Can you go a little down? Yeah, this part actually, I mean, based on this concept only, the other, I mean, in the upcoming slides also, the professor
Yes.
has explained.
Yes.
I was able to construct the other models, but the output I was not able to get the intended output for even for the basic one also, like this one.
Okay.
So,
Okay.
yeah.
Fine. So we'll actually try it right away.
Okay.
Fine. And what else? Like so. So then in this uh, part, like they have basically covered first simple pendulum, the non-linear model without any aerodynamic drag, and then they have introduced various kinds of aerodynamic drag. So firstly it was with considering like a constant aerodynamic drag force FD here, and then using that, so they build up this model. And so the key thing that they are using is this sine thing, so which is
Yeah.
basically the concept that the uh, drag force should be opposite to the velocity. So
Yeah, this part also based on the sign
yes,
block which was being introduced here.
yes, yes.
So this sign part, how it takes care of based on the velocity. Uh, I mean, it should be opposite. How it will take? I mean, do we need to give some? Not only the velocity, do we need to give anything in that block definition?
So okay, fine. So we'll look at it.
Okay.
So let us first go through the. So are you able to see my uh,
Yes. Able to
MATLAB
see.
screen?
No, not MATLAB
Not
screen.
MATLAB
I'm
screen.
able
Okay,
to see the slides. Yeah.
okay, okay, fine. Let me just share it again. Okay, fine. So I have opened MATLAB now. So I hope you are able to see my MATLAB screen, right?
Yeah.
Okay, fine. So yeah, so are you just let me know whether you are able to see this properly, or should I increase the font size a little bit? Yeah, yeah, I think this is better.
Yeah, this is fine.
Yeah, okay, fine. So then we'll go step by step, and so first we'll just create a blank model. So yeah, so now then, to initialize this model, we need to have like some parameters that are used in the model. So let's basically g acceleration due to gravity, then the length of the pendulum. Let us say we use it as 1 meter, and let us say the initial angle by which it is displaced. So let us say it is minus 60 degree. So I'm saving this MATLAB code as simple pendulum init, so that when we are using this Simulink model, we can just use these parameters from the MATLAB workspace. And then I'm saving the Simulink file as simple pendulum nonlinear. Okay. So the first thing is uh, in this equation, let us go to our basic equation. Theta double dot is minus g by L sine theta. So our acceleration theta double dot is minus g by L sine theta. So basically we need to integrate the acceleration, basically the angular acceleration twice to get the this thing, like basically the angular acceleration. So we need to integrate the angular acceleration twice to get the angular displacement. So then we'll use this gain block, and
Does the gain block means, is it a scaling one?
so it will just scale the signal.
Okay.
Yeah. So now basically we need to integrate this twice. So there will be an integrator here. So this, so like let us say the input to the sine block is theta. So sine, so also the output here will be sine theta and g by L. So it's actually minus g by L sine theta. So we'll basically, so this output of this gain block will be the acceleration. Now we integrate, so this output will be basically theta double dot. So then once integrating this once, we will get the angular velocity, and integrating it twice, we will get the angular displacement. So here we initialize this to this value of theta naught. Okay. And So this is basically theta, and this goes into the sine block. So essentially this itself is the model. Now to visualize the signals, we can, I mean, so here, so in this they have used two gain blocks. So we can actually, in our case, we have just, combined it into one gain block of minus g by L. And so integrating it once is the angular velocity, and here integrating it twice is the angular displacement. So then we'll put a scope here, and we'll convert. So these theta values will be in radians. So we can convert them into degrees by multiplying by 180 by pi. So then we'll get here the angle made by the pendulum with respect to the vertical in degrees. Now we can set the stop time to, let us say, 120 seconds, and let us go to the solver settings. So if we generally, like, what approach that we can follow when we like have a certain model, so we can allow MATLAB to select the appropriate solver based on whatever models. So we can use automatic solver selection, and then the step sizes and everything. So we can set it as auto initially, and with the default settings. So let us try running this model and let us see what output we get. So there was no error. So yeah, so here we can see that there are I mean certain oscillations with variable amplitudes and all. So we are not sure whether this output is actually makes sense or not, because so when we set it to auto, so here, yeah, once we run the model, sorry, so yeah, once we run the model, we can see that it has selected OD45 as the auto, so like by automatically it has selected OD45. So generally this is a robust solver, like robust nonlinear like differential equation solver. So like the first thing that to try would be like OD45, and then uh, so we can observe the output of this. It looks slightly weird because it's showing some sharp, like the curves are very sharp. So then in reality the output won't be like this way. So then we might consider changing the step size. So it has selected, so if we hover the cursor over here, we can see that it has selected the maximum step size as auto 2.4. So are you able to see that?
Yeah.
Yeah, so then we can actually try to tweak that. And so this doesn't seem to be that good. So then we can actually try to reduce the step size and then try to rerun the model. Yeah, so this looks much better. Uh, so at least this output seems somewhat, tending towards sinusoidal, but still, we can see some sharp edges. Like, so this step size is still not good enough, because, it's showing some sharp changes. So what we can do is we can actually reduce the step size further. and then let us say we'll try with 0.01. So since there is no damping present in this system, so we would expect that the amplitude to remain mostly constant. So now since this is uh, the initial displacement in this case was minus 60 degree, so it won't behave like a linear pendulum kind of case where for where we invoke that small angle approximation, but essentially we would expect that the amplitude of whatever the signal should be more or less like uh, constant and should seem somewhat like sinusoidal. So this seems reasonable and the curve now looks much more smooth. So we can actually just reduce the stop time to 10 seconds and try to rerun. Yeah, so we get this kind of an output. So does that make sense?
Yeah, actually now I'm able to get it. The mistake I've done for the G by L parameters you defined, right? For the G by L and the theta naught.
Yeah.
So, uh, so actually the how it will take from I mean in the from the MATLAB environment this
Mhm.
how it will read actually. I mean we have to save it as a separate file and you're running it in the same.
So we can like there are two, three options. One is basically just you can create a script like the way I have created a new script and then
Right.
type in whatever parameters like let us say G is 9.81 meter per second square, length of the pendulum, and then the initial displacement. So these are the only three parameters, and then we can just run the script, and then what it will do is it will initialize the variable
Okay.
variable values in the workspace. So now when we use these parameters in the Simulink block, so it can pick the pick up the relevant values of these parameters from the MATLAB workspace.
So after writing the after writing the saving that .m file,
Yeah.
then you have to launch the Simlink window, right? Then such that it can read that generated variables in the
Yes.
workspace.
Yes. Yes.
Okay.
Yes. Yes.
Okay.
So in addition to that, so you can have another option. So you can actually create a dot mat file. So let us say if we uh, create a like let us say if we have these like three parameters here and so those are of our interest, so then we can save these um, variables into a .mat file, mat file. So then we'll give the name as simple pendulum init .mat. So now we have created a, so you can see here on the left hand side, so you can see this simple pendulum init.mat. So that file contains the information of these variables. So what we can do is, so instead of uh, creating the script and running it, we can just uh, load the variables in. So what we can do is just right click on that and say load, or like if you want to write it as code, so then we can just say load this file name .mat. So that is another option. And the third option third option can be like we can just instead of having this as parameters, we can just type in directly the value of that parameter here itself. But then if we want to change the parameters and then try to rerun the model, then we have to again go inside each and every individual block and then change change the parameters. So to avoid that, we can have the parameters part separate and then use this model, like it becomes more modular in the sense that we can just change the parameters and rerun that model. So the framework will remain the same, just the parameter values you can change it. So that is one way to do that. And further, going further, if we want to, you know, even avoid this manual work of, um, loading the kind of variables, either like using the mat file approach or using the script. So what we can do is, so we can go to, so in the Simulink model window, so we can go to the modeling tab and then go to the model explorer and then go to model workspace. So here the model workspace thing is basically, it's kind of a MATLAB workspace which is uh, specific to that model itself. And so whatever variables or parameter variable values, so it can load the values in the uh, model workspace instead of using the basic like base MATLAB workspace. And then, so here we can set how to initialize the I mean the model workspace. So we can provide a data source. So let us say if you want to use the mat file approach, so then we select data source as mat file and say file name and then say select this simple pendulum init and say open, and then now it has this reinitialize from source. So then what it will do is, if I say that, then it will load these same parameter values in the model workspace now. So now then, even if the base workspace does not contain any information, so we can still run the model. Just we can just open the model and directly just uh, run it. So whatever required variables are already, the initialization part of the parameters is already taken care of. And then if we, so now if you observe, so there are no uh, variables in the base workspace now. I have cleared it. And if I now run, the model will again run without any error. Why? Because it is already having the relevant parameter information in the model workspace. So this is how we can create uh, models which become more or less in, like if we have multiple sets of models to run, and then each of them have the parameters may be same but the values may be different. So what we can do is like create a relevant mat file for every model and then load it in its own model workspace so that there is no conflict in the base MATLAB workspace. So each model can run individually without any conflict with each other. So does that help?
Yeah, understood.
Oh,
Thank you.
yes. Now going further, we can try to add this particular aerodynamic drag concept here. So now what we are doing is basically we are our differential equation is basically theta double dot is minus g by L sine theta, and this value of this drag force by ml. So let us say we introduce this drag force and m is, let us say, 1 kg. So now here this is our acceleration, so there will be additional terms now which will come in. So now to, so in here we are considering a constant force. So we will Fd into m into L upon, so that is our the required value of the uh, drag force related term in the angular acceleration. And so we can now add these two together. So we will add minus g by L sine theta and this Fd by ml, and then we'll again follow the same approach of integrating it twice, and then now in addition, so this we have used Fd by ml, and then um, so we are missing some more terms actually, so it should be minus Fd by ml. So we can use again a gain block to invert its sign, and then there is the concept of that the value of the uh, drag force should be opposite to the angular velocity. So the angular velocity part is coming up here. So then and then we'll multiply this sign, and so this is our actual damping force. So the damping force will be opposite to the uh, velocity by using this concept. So here we are getting the angular velocity, and then this is finding out the sign of that, and then we are introducing it here like this way. So now let us try to run this model now. So there is some issue with the zero crossing detection part. So let us now leave it to the step size part to auto.
Sir, I have a question. Can I
Yes,
ask?
yes,
You
yes,
just said your angular velocity has to be opposite to the drag force,
yes, yes,
right? What the sign block, when I studied about it, is it is going to return if it is plus one, it returns plus one. If it is a minus one, it is going to return minus one. So
yes,
when you
yes,
have put there, are not just taking the sign. You need to do something to change the sign, right?
yes, yes. So we are already saying this minus
Oh, okay,
fd
okay.
by ml,
Because
and then reversing the sign. Like, so let us say if it is the angular velocity is positive here from this block, then by multiplying by minus 1 we are actually reversing it, so that way. So there is some problem with this model.
maybe the values are not consistent for the calculation purpose.
Actually, at the end of the presentation, professor has given some values. Maybe we can try with that.
Okay, so the parameter values.
Yeah, yeah. He has given some. One, yeah, this is a.
Okay, okay. So it should be very, very small. Okay, okay, we can try that. So maybe the parameters are like, we have not considered the right combination of parameters here. Yeah. So now we can see at least some output here now, which is oscillatory, and then we can further try to tweak this value of the force, and yeah. Now it is using a maximum step size of 0.4. So we can actually now consider reducing it. So generally when we are running a new model, we can, it's a like, good way to good starting point to just set um, max step size to auto. Yeah. So here the damping is actually not much. So what we can do is we can try to increase this force. Yeah. So this is now looks much more like the Coulomb damping kind of case, where we have Coulomb friction, which is constant in magnitude but opposite to the sign of velocity. So this we can see a linearly decaying trend in the amplitude.
That
Yeah, I cannot hear. Actually, I cannot hear you. I still cannot hear you properly. So can you just type in whatever your question is in the chat? So I'm not
Sure.
able to. And now I think the next part was to include the aerodynamic drag, where the drag force is proportional to the square of the velocity. So we can also try to incorporate that in addition to whatever that uh, constant uh, drag force. So now to incorporate this um, viscous drag like force, so uh, we can just create a u square kind of where we use the angular velocity square and then some constant. So we'll not get into the details of how that this drag coefficient and all that. So that's a separate thing in itself. So but let us say if we are given some, so let us say take some trial values of the drag force, like the constant for the viscous drag force. So let us say it is 0.01, and it's again minus. So again it will be opposite to the sign of the velocity. So we need again that same um, product block. So we'll create another additional port for incorporating this viscous drag force. So it is some constant into velocity square. And then let us try to run this model again. So the output looks somewhat similar. So we can try to uh, induce the effect of increase the effect of the viscous drag. So now we can see slightly more of exponential decay in addition to linear. So the damping will be now a combination of linearly decreasing amplitude and combination of exponentially decreasing amplitude. If we I mean remove this part uh, of the Coulomb damping part, so then we will just see pure exponential decay of the amplitude. So let us now again further increase the viscous damping force. And yeah, so now we can see that the effect of viscous damping is more um, present in as compared to the Coulomb friction. So in this way we can actually just try to tweak the different parameters and see how they impact the behavior of the model. So does that make sense?
Okay.
Okay.
Sir, the sign is getting uh, connected. The sign is getting connected after the second integrator, whereas the drag force you have connected it after the first integrator.
Yes, because it is the drag force is proportional to the square of the angular velocity. So
Okay.
then after the first integrator, so this the input to the integrator is acceleration, angular acceleration, and then the integrator output is angular velocity. So we are taking this angular velocity, squaring it, and then uh, expressing this as a drag force likewise this way. And then also we are using the concept that the drag force should be opposite to the angular velocity. So we are using the sign block here also. So is that okay?
Yeah. Okay, sir. The X block there means multiplication. Is that right?
Yes, this is product.
Okay.
And yeah, and what was the other query, Mr.
The decaying is due to the drag force. Is that
Yes, yes. So the decaying is due to the drag force. Yes.
okay?
So
Yeah, on the holonomic constraints.
okay. So I'll again just put up the slides. So I'll try to answer your question to the best of my knowledge. But yeah, so are you able to see my screen where I'm sharing the slides for the wheeled mobile robots?
Yeah.
Okay. Yeah, so just let me know. I'm just scrolling through the slides. So just let me know which part you were not clear about.
Yeah. Here, that constraint they're talking about, that non-holonomic and holonomic constraints.
Mm-hmm.
That means it cannot be integrated. Means I was not able to understand this part actually.
No,
Uh,
so yes, yes. So I think this is more of a mathematical explanation. Physically, as per whatever my understanding is, like where holonomic um, and non-holonomic. So what physically I think we can uh, try to explain like what it is I think holonomic means that we can uh, the steering motion and the forward. let us say the translation motion of the wheel, point of contact of leg. So so that is, it can be independent. So so this omnidirectional wheels, so those can in some sense be lead to holonomic kind of motion. So where the, like let us say if we have a car which has these omnidirectional wheels, and now if we want to use it, these kind of wheels to park the vehicle, so we can just uh, go just beside a parking slot and then just slide sideways. So the wheel rotation axis and the sliding motion axis, so it can be 90 degrees. So I hope you are able to visualize what I'm saying. So it can just slide sideways 90-degree to its axis of rotation of the wheel. But in where we have a simple wheel which is rolling without slipping along some path, so then there so since there is no slipping present, then the motion has to be along the tangent to the path. So basically the instantaneous velocity of the wheel should be always directed along the tangent to that path. So there will be no sliding motion sideways perpendicular to that path. So physically that is what I think it means. And then how we can say it mathematically is this equation: x dot sine phi minus y dot cos phi is equal to 0. Then so what I think they are calling as this f of x, y and phi, I think. So even I was not really clear about what they exactly want to say about this, but what I think this is that um, this is that function f of x, y and phi that they are talking about, and that is not integrable. But I am sorry, I cannot really provide you a mathematical explanation on how um, this can this how exactly this comes about. So I am actually not really do not have much knowledge about this concept.
Sir, would you mind if I add a question?
Okay.
Recently, we have completed a wheeled robotics course.
Okay.
What the professor? There, the professor explained about holonomic and non-holonomic. If you
Okay.
are standing behind your car and
Mm-hmm.
if you push it, it will go forward. But
Yeah.
if you come towards the side where the door is, and if you try to push the car in the other direction, it won't move, right? If every
uh,
one of us is standing behind the car and we push it, it will roll forward.
yes, yes, yes.
But on the side where the doors are there, if we start applying for stand on that side and start pushing it, the car will not move because the friction in that direction will be too much.
Yes, in a way you are right. Yes.
Right. So when it comes, so every object will have 3 degrees of freedom: x, y, and rotation.
Yes.
Whereas the car can take a turn or can only move
Yes.
forward. It is a non-holonomic.
Yes,
Whereas
it
if
is
you
not.
take
Yes,
to
yes.
watch the videos on Omni wheels or Magnum wheels in
Yes, yes.
YouTube, they
Yeah.
will show these robots can move in the x direction, y direction, and they can also rotate.
Okay. Okay.
So all the 3 degrees of freedom they can achieve, but for some they cannot achieve. Like the car, I'm telling, a
Yeah,
car
yeah.
or if you take our auto, they can move only in the straight or they can
Yes.
take a turn
Okay. Okay.
because of the wheel configuration and how the sliders are arranged. They can move in X direction, they can move in the Y direction, or they can move there and then themselves. You can watch our videos in YouTube.
Okay. 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 Sure. Thank you. Thank you. I'll definitely try to look at that. Sure. So, anything else that we had to discuss on the lecture slides or anything like that?
Is the software shows it is for trial version. Because you are at IIT, you get a free version forever as long as you're in IIT.
So because I am affiliated to IIT Bombay, then I get a educational license, access to an educational license of MATLAB, which is valid till I am there in the institute.
Okay, yeah.
But for you, I think the course participants, so it's there till the course is going on. So hopefully you have access to MATLAB, right? At least for the
No,
duration of the
no,
course.
I did not try. Earlier in one of the
Yeah.
course, it has given MATLAB access. The next course when I come in, it did not permit me. I said, okay, leave it.
Okay.
That's why I have not tried it this time.
Okay.
Yeah, I'm able to access it.
I see. Okay.
I'm able to launch
Okay.
it. Yeah, for the skin Simscape part, actually, the libraries whatever that are mentioned in the lecture,
Yes.
actually I'm not able to launch that Simscape window actually.
Okay.
Like how to, 'cause I'm not able to construct that model whatever that was.
Okay.
Able to
So
understand that four bar mechanism, but is not somehow not able to launch the Simscape window.
I see. I see.
Somewhere
Okay.
I'm
Fine.
missing some part in that.
Yeah. So what you can try to do is this way. Like if so, you have an offline copy, like kind of desktop copy of MATLAB, or like you need to use online MATLAB or something.
Here I'm using an online MATLAB version. I mean, whenever
I see.
we launch the version using that Access window, it
Mm-hmm.
is showing the MATLAB online.
I see.
So,
Okay.
like if you at the top of the window, in your window, it is showing as academic use, right? So
Yes.
there
Yes.
for us, it is showing as like 2024 online, like it is
I
coming.
see.
There
Okay.
is an option it is giving like we can download the version of MATLAB.
Yeah.
But, I think the license access was given till May 13th.
I see.
That
Okay.
is the maximum
Okay.
date. I
Okay.
think for 1 month it was given. I think I launched the MATLAB version. I think just some 1 week back. So I think
I see.
probably I think 1 year. I mean just more than 1 month it is giving access. Yeah.
I see. Okay. Okay. Fine. So I think in the online version of MATLAB, you should not face the problem of toolboxes missing or something like that. So if you have an offline desktop kind of version, then you need to actually manually install the toolboxes, whatever you need. So if you want to, in an offline desktop version of MATLAB, if you want to see which all toolboxes are already installed, we can just type VER in the command window. So it will show what all toolboxes we have installed. So it will show the whatever version of MATLAB or uh, and then it will show, like let us say I have Simscape installed and like other kind of toolboxes. So you can, if you have an offline desktop kind of version, so you can try to this VER command. And if you want need to install that toolbox, so you can go to add-ons. So you can see this add-ons kind of thing. So get add-ons and then type Simscape. So then you can see like there are multiple uh, Simscape toolboxes, like for different domains, analysis domains, so like fluid mechanics or driveline dynamics or whatever, multi-body dynamics, electrical, whatever, etc. So whatever, so those kind of toolboxes you can get it by using this add-on thing. And once that is installed, so you can actually get access to the Simscape. Now the issue I think you might face with respect to the thing in the, whatever uh, the things that are mentioned in this lecture slide, where they are mentioned, like click on this, that like the um, enter these parameters and that parameters for simulating the 4 bar mechanism. So these things are, I think, for a very old, like older version of MATLAB.
Okay.
So this, like it's mentioned that sim mechanics kind of something, like where professor has mentioned, I think, sim mechanics somewhere. So it's now called as SimScape Multibody. So earlier it was called sim mechanics. So the user interface might have changed. So yeah, so this is sim mechanics kind of thing. So it was earlier known as sim mechanics, but now it is called as SimScape Multibody. Uh, so so I think you can uh, refer to the latest documentation for this toolbox. So which you can get access through online or whatever. So you can say doc SimScape Multibody or whatever. So then you can get the latest documentation in that, which is corresponding to that version. So then you can, I think, it will be easier for you to access whatever the blocks that are. So I had planned to demonstrate a example of analyzing the vibrations for a simple spring mass damper system using Simulink, and same thing using SimScape. So hopefully that should help you get started in with SimScape. So shall we go through
Okay.
that?
Yeah, maybe you can go to that. Yeah,
Okay, fine,
that would be useful.
fine. Okay. So then, yeah, let me just.
Sir, regarding holonomic and non-holonomic, I
Yes.
have pasted the NPTEL link in the chat box. If you go and see that course,
Okay.
week 2, lectures second and third, you will get a idea on that.
Okay. Sure. 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 Thank you. Thanks. So let me just. Uh, so I'm just sharing my screen. Yeah. So let us talk about the simple spring mass damper kind of system. So we have so the differential equation that we will get for this spring mass damper system. Let us say the spring constant is K and the damper coefficient is, let us say, C. Then we'll get the differential equation as. Now if we want to, so I'll not go into the derivation part of this. So I think we have already gone through this. So So we can just assume that this is the differential equation that we'll get. So we will if we rearrange this equation, so we will get yeah. So this is the rearranged form of equation. So now we can use this in for our Simulink or whatever Simscape model now. So we will have to integrate the acceleration twice to get the displacement x. So we will now move to the MATLAB. Yeah, so this is our MATLAB blank Simulink model. So I have already created a script to initialize the parameters. So the mass, stiffness, and damping coefficient C, and the initial displacement of the mass x naught. So what I'll do is I'll just initialize these variables in the workspace using the script. So now we have the relevant parameters in the base workspace. So now we can start creating our model. So our differential equation was that x double dot is minus c by m x dot and minus k by m x. So let us let us say the output of this is x dot. So x dot into minus c by m. So this is the first integrator, and then we will integrate further this velocity. So we take a branch out from here. So this is our displacement x. So we can say here is x, and this is, let us say, x dot. And then we will add these two things. So minus c by m x dot and minus k by m x. So this is our x double dot, which we will give it to the integrator. So this is x double dot, or basically the acceleration. So we are mainly interested in the displacement. So we can create a scope to plot the displacement. So I'll save this as spring mass damper Simulink. So here in the for the displacement, we have our initial condition as x naught, and the initial velocity part is 0. So our initial condition is 0 for the velocity. So we are all set to run this model. Now the next part is our selection of the solver. So as mentioned earlier, so we will first try to solve with whatever default the default auto solver selection, and then see if we need to alter the step sizes. So it used a step size of 0.4, and let us have a look at the output. Yeah, so this is the output. So let us so the motion is getting damped before 10 seconds itself. So we can have a look at the output. So this is how the output looks like. So we can see that the curve is not smooth. So we may need to reduce the step size further. So now what we can do is we can say 0.01 as the max step size, and then try to rerun. Then we should see a smooth curve now. So this is the typical type of response that we would see for a damped viscous damped uh, spring mass damper system. So just excuse me for a minute. Yeah, yeah. Sorry for the disturbance. So this is how we can
Uh,
solve the yes.
Sitting for a 2 hours discussion like this will be very difficult for everyone. So I think should always take a break of 10 minutes in between after every 1 hour.
Yeah, yeah, sure. So we can definitely take a break of 10 minutes if you want. So do you want a break now?
No, I am okay with it.
So Mr. Ravikiran, so do you need a break now?
No, sir, you can carry on.
Okay, I see.
So if you can stop for 10 minutes. Otherwise, we'll continue.
Okay. No, I think I'm okay. We can just get going. Like, I think we can continue. So this is how we can get the output for like using Simulink for a simple spring mass damper kind of system. So is this okay? Like the spring mass damper using Simulink part?
Yeah.
Okay. So now the model building for the Simscape part is like somewhat easier, because then you can just create physical connections the way, so you have a simple spring, mass and damper, so you can just look for, like, mass, let us say mass. So then, here we'll get many results, but this I think is the relevant thing. So in the translational elements part in the mechanical, so in the Simscape library, so you can go to the foundational library, then go to the mechanical uh, library, and then use go to translational elements. So there we can find the uh, block for mass. So then we'll add a block for mass, and the mechanical translational reference, so that we need it for selecting what is our, like, let us say there is a fixed kind of, like the mass is, like, let us say, mass, spring and damper, like there is a fixed reference that we are measuring the displacement with respect to that, so that is given by this block. Then the next thing is selecting a translational spring. So this is the block for a translational spring, and similarly we need a block for a translational damper. So for both, so we can rotate these blocks for as like the way we need. So let us say we rotate it this way. Yeah. So then we can flip this. So we need to just connect these things physically. So like the way they would be connected in reality. So we need to just join this spring, mass and damper kind of thing. So that's it, like in terms of the physical arrangement. So let us save this. So this is our basic model of, like, with where we have the physical connections. Now to read data, like the signal values from this, there we need to do some more uh, modeling effort. So we need to select first a solver configuration block, and then a PMC, physical modeling connection port. So and in order to read the displacement or velocity or whatever, we need this ideal translational motion sensor block to read the um, data, like the sensor, whatever the actual values of the displacement or velocity or whatever. So So we can go inside the mask block. Let us say we use the value of m, which is already there in our workspace for the mass. Then for the spring constant, so we can and use the value of the variable k, and for the damping constant, so we can use the variable value of c. So we need to get a port block also into this. So I'm just searching for that. So it's basically this block. So PMC and port.
What is that port used for actually to?
So it is basically to create to we need to read out the like let us say the displacement, velocity or acceleration or whatever thing. So from the physical system, so we need to convert the physical systems into a Simulink readable time-based signal that we can see like with respect to time how the signal value is changing. So in order to get that, so we need that port.
Okay, sir.
Yeah, so I was not able to find that port for some reason. So yeah, so this port. And we also need to convert this physical signal to Simulink converter. So then so this is a solver configuration block, and this output is given to this block, and it this thing measures the relative velocity or relative position with respect to some reference, so which is provided in the C port. So again we have this translational a reference block. So we can use the same thing here. And so this port C is grounded. So this is somewhat non-intuitive and like, but I think it's some kind of procedure, or you can say syntax for this, this language of Simscape, or whatever it's called. So but essentially what we are doing is getting the so this has two ports, like the initial position x naught is given to this block, and then we are reading this position, so we can also read the velocity here from this port. And so we will get the output of the model in a single variable called as out simscape. So we are setting it likewise, and similarly for the other model that we had created. So for the spring mass damper system using Simulink, so we can again say 2 workspace, and now we can name the output variable as out Simulink, so that we will be able to easily differentiate between which output is corresponding to which model. And so this is a 2 workspace block, so whatever is the output of the model, so it will store it in the base workspace as this variable. And so it will create an object named out Simulink, and inside that there will be a variable x. So if we run the model, so we will get this objects like out Simulink. And then for the Simscape model, so I think there is some issue with this. Yeah. So we have now the outputs of both the Simulink and Simscape model. So we can compare them in by plotting them in a common common figure. Should be exactly identical. Okay. Okay, so then I think there is some issue with the initial position thing, but basically the results are basically the, so there is an offset in the deflection plot that we have, like we get from the Simulink model and the Simscape model. So if we can adjust that offset by adequately adjusting the parameters in the blocks, but essentially with the behavior we can see that it is the same for both the Simulink and the Simscape models. So this is how we can create physical models using Simscape. So does that help?
Yeah. Yeah, now I'm able to figure out the Simscape windows. I'm able to draw the elements and all. So
Okay, okay,
I tried, so I was able to
okay,
do it now, at least half of it. Yeah, whatever you have done.
okay,
Thank you.
okay. Yeah, welcome. Yeah, so, fine. So then, uh, so that's all that I had from my side to demonstrate regarding the how to use MATLAB, Simulink, and Simscape. So I had also prepared some simple uh, problems, which would be, I think, similar to what the kind of problems that you would see in the assignments. So shall we go through that quickly?
Yeah.
Okay. Just let me share my screen. So yeah, so let us go through these questions, which are somewhat similar to the kind of problems that we would see in the assignments. So in this first question, it shows the picture of a Simulink block. So what do you think this Simulink block do?
The final value of a signal it will show.
Yes, it actually just displays the value of the signal. That is true, but
Okay.
uh, so I think in during any instant of time it displays the maximum value of the current signal.
Oh, okay. Okay.
So the correct answer is A. Now, so the block which is shown here, what do you think it does in Simulink?
It's a delay.
Yes, it is a delay block. So it just gives the value of the signal one time step before the current time step. Then the extension of Simulink files is what? So which one do you think is the extension of Simulink files? So it's basically .mdl. So that was one of the older versions of Simulink had like used this .mdl kind of extension, but now the modern versions of Simulink generally have the extension.
Now it is the it is dot m and dot.
Yeah, for Simulink, the model has the extension
Dot,
of
yeah, sorry, dot SLX.
.slx. MATLAB scripts use .m, so that's how it is. Yeah, so I think this question may take some time to go through the derivation part. So let us keep this question for later, and we'll come back to it later. So let's just cover the simpler questions. To deploy models to other simulation environments, the Simscape multibody supports which code generation? So are you aware?
C.
Yes, it is C language. So we can build or generate basically C code from the Simscape model. Which of the following statements is not correct?
I think second B1. I think it is
Yes, yes, it is correct. So the actual degree of freedom is just
one.
1.
Yeah.
So this shows a figure of this wheel where the axis of rotation and the wheel, basically the wheel is moving along the tangent to the path, and the equation is given. So which kind of constraint is this?
Yeah, I think it is the B, right? Non-hollow.
Yes, it is non-holonomic. So there is a sequence given here in terms of for modeling. So and then there is a real world system, there is a conceptual model and a simulation program. So the thing that we do between basically the conceptual model and real world system, what do we call it?
Validation.
Yes, yes, it is validation, because we compare our conceptual models. When we compare it with our real world system, then it is called validation. And then similarly, when we compare the simulation program with respect to the real world system,
That also validation.
that, yeah, exactly, whenever we are comparing with respect to the real world system, so that is also validation. But now when we are comparing a conceptual model and a simulation program, so then that we can call it as
Yeah, verification.
verification. Yeah. So the correct answer is validation, verification, and validation. So option B. So which one do you think is the correct answer to this question?
I think all, right?
Yes, it is true. The all the options are basically techniques for validation of simulation models.
Okay.
Yeah, so that's all in terms of the simple multiple choice questions that we had. Any other thing that we had to discuss?
No, sir, that's all. Maybe we can go through this problem.
Okay, fine. Fine. So then we can look at this problem. So it shows an inverted pendulum mounted on a motor driven cart. So the pendulum can move only in the plane of the paper, and the center of gravity of the pendulum rod is at its geometric center, and this force U is applied on the cart. So we have to find out the equation of motion for this inverted pendulum basically. So we will first make one assumption that this surface is then let us draw the free body diagrams for each of these components. So let us first draw the free body diagram of this cart. And then let us say there is some force force in the rod. Let us call it as some tension T, so which is acting at an angle theta from the vertical. And then there is another force U. So the displacement of the mass M along the x direction is denoted by x, small x. So then the equation of motion for that is basically So along the x direction, let us use the so the sum of forces along the x direction will be p sine theta plus u is equal to mx double dot, and then if we draw the free body diagram similarly for this mass, the so the equation of motion along the x direction, so this will be, let us say, x direction and this is y. So t cos theta minus mg, so the y coordinate will be basically L cos theta, so here y is actually L cos theta, so y double dot will be equal to minus L cos theta basically. And the equation of motion similarly along the x direction will be basically minus t sine theta is equal to m uh, the so the position of the center of mass of the uh, rod, or it's basically x plus L cos theta. So these are our equations of motion. So we can further use some more algebra, like let us rewrite these equations here. So this is actually not correct. So y is equal to L cos theta. Y dot will be minus L sin theta dot, and y double dot will be minus L cos theta dot square minus L sin theta double dot. And then minus t sin theta is so the double derivative of L cos theta. So we have already written that. So it's same as y double dot. So what we can do is then we can eliminate this variable t and then simplify these equations to essentially get two equations of motion in terms of basically either x and theta or y and theta or whatever. So uh, so this is how we can get the equation of motion. So I will not really go into the algebraic simplification of that, but this is basically the process that we can follow. So is that okay?
Yeah, got it, sir. Actually, the basically the capital M, that is the cart mass, sir. How you simplified actually?
No, I didn't get your question.
Basically, the last. Can you go to the next slide?
No,
Here.
I didn't simplify anything with for the cart mass, like cart, the equation of motion for the cart.
Okay. Okay.
So that's all that I had from my side.
Okay. Actually, here there will be two uh, accelerations. That is the cart acceleration and the rod acceleration, right? That x double dot
Yes,
and
yes.
okay, like two
So
variables.
there will be terms corresponding to x double dot, and then there will be corresponding terms corresponding to the theta dot and theta dot double dot. So all those kind of terms we will get in the second and third equation. So we can simplify it to eliminate t by using various algebraic operations, like for example, we can just use the last equation and substitute for t from that, and then use that value of t in the other differential equation. So that should uh, kind of serve our purpose. So like, so and then we can plug this into these equations and then simplify it further to get basically two equations of motion. So the degrees of freedom here will be basically x and theta. So there are 2 degrees of freedom, so we should get 2 equations of motion. So by eliminating t, we are reducing these 3 equations of motion into actually 2 because they are not independent. So that's about this thing.
Okay, got it now. Yeah.
Sure. So that's all that I had from my side for this today's session. So if there are no other questions, so we can close this session for today. Thank you very much for joining.
Yeah, thank you very much, sir. Yeah, for clearing all the doubts. Yeah.
Sure.
Thank
Thank you.
you.